Hello, BC Calculus students. This is Mr. Johnson, and this is section 7.4, which is on exponential growth and decay. And this is a very short video, so we'll practice more of this in class, but this gives you the overview of the idea behind the exponential growth and decay connected to differential equations. So the first thing is that one of the ways we can analyze population is that we can look at the rate the population changes based on population size itself. And one of those models can be a directly proportional model, which basically means that you multiply by a constant k. So if we look at the rate the population changes based on this constant k times the population itself, this can give kind of a short-term or a short period of time approximation for the population itself. In other words, if a population is big, it will be increasing at a larger rate because it's already a large population versus a small one increases at a slower rate of change. Clearly, we're not taking into account other factors that we will look at when we talk about logistic equations. So we're going to solve for p here by using our differential equation approach, where we separate our variables, and then we will integrate both sides. Now, we do get the natural log of the absolute value of p, but since this is population, I'm going to leave it as just p. We add our constant. We don't have any sort of initial population right now, so we're going to leave our constant the way it is. And then I'm going to solve for p by taking e to the power of kt plus c. And I'm going to rewrite that as e to the c times e to the kt. So I'm going to use properties of exponents there. Now, if we have let's say we have an initial population of, let's say it's just p sub 0. Okay, so that would be at time 0. Then we could take our equation and say that we have p sub 0 equal to e to the c times e to the k times 0, so e to the 0, which obviously gives us just e to the c. So this e to the c in the context of population, so this particular example would be representative of the initial. So your general population model, again we're solving for p, is going to be the initial times e to the kt, and again that k is the value that denotes the change in population as a constant value. So this has a couple implications for half-life or doubling time, that type of thing. So for example, let's say we take a look at half-life. That means that half the initial would be our result, and we could cancel the initial population on both sides of the equation, and we could take the natural log of 1/2, which gives us k times t. Now you may have to solve for that constant k. You may have to solve for time, and in either way you have this equation that relates the two of them. So if I needed to solve for k and I had the time, I could divide by time. If I had the opposite, then I could find the other variable. Let's say you have a doubling situation. That means that the initial population would double, and we could again cancel the initial, and we have the natural log of 2 equal to k times t. Now you notice this pattern that's forming. Hopefully you notice the pattern is forming where we have half-life and we would have that 1/2 there, and we would have doubling and we have the 2 there. So if you were to triple something, or the fifth life or something like that, you would have the exact same type of relationship. And what this does is it allows us to figure out that constant k or that time t depending on what we're given. So there are a couple examples on this. This is not a major topic on the exam, so we have just a little bit for you. We'll practice some more in class, but this is the idea of the differential equation connection to this growth and decay. Thanks.